in this session, we will look at another important application, that of text compression. Text compression as such is a very crucial idea used extensively in security as well as transmission of data. So, text compression is a very important idea used in applications. So, given a string x, we want to efficiently encode x into a smaller bit string y. Let us assume that the x string that we want to encode is made up of characters from say English alphabet or English language. What we want to do is to encode x into a bit string, that is a string containing zeros and ones and whose length is going to be smaller. So, it is going to be encoded such that the size is smaller. So, you also looking at security in the way that you are encoding the information and also looking at transmitting data so that the size is smaller. If you look at English language and encoding into bit strings, there is a very simple brute force solution. We know that there are only 26 alphabets or characters in English language, and if you use 5-bit strings, a string with 5 bits, then we know we can have 32 distinct such 5 length bit strings. So, each alphabet can be represented by a bit string of length 5. So, we can just keep on starting from A, which can be represented by 0, B by 0001 and so forth. So, for example, when you are doing a 5-bit encoding of English characters, A can be encoded as 5 zeros, B can be encoded as 1, whereas C can be encoded as and so forth, and you can continue this until Z. So, if you have 5-bit strings, then we can encode every character of English language. Such coding schemes are called fixed length codes. The difficult question is whether we can find a coding scheme in which fewer bits are used. We saw that fixed length coding schemes, the number of bits that we are going to use is going to be remain fixed, which is decided, whereas what we want is to reduce the size of the, or we want to use fewer bits to encode the strings. So, the answer is to use what are called variable length codes, that is alphabets which are going to occur more frequently, that means characters or alphabets that occur more number of times in the text that we are going to encode, typically should have short bit string representations or should be encoded by bit strings of shorter length, whereas alphabets which are going to occur rarely or are not so frequent can have longer bit strings. So, these are called variable length codes. Let us try to illustrate this with an example. Now, suppose we have a file which has this many characters and which contains only the alphabets A to F. We also know that the frequencies of all these alphabets in the file. So, we see that this frequency is in thousands, frequency in this is frequency in thousands. So, A is occurring 45,000 times, B is occurring 13,000 times and so forth, and F is occurring the least number of times in the data, which is 5,000 times. So, we look at both the fixed length coding and a variable length coding. In the fixed level coding, since we have 5 alphabets, we will require 3 bits to code them. So, we use 3 bit strings and we use A as 000, B as this and 5 as 101, F is encoded as 101. So, if you have a file with 1 lakh characters, the fixed length coding would require 3 lakh bits to code the file. Whereas, if we use a variable length coding, so the one which is going to occur most is going to be represented by a bit string of less length or smaller length. So, A is going to be represented by only by a 0, whereas B is going to be represented by bit strings of length 3, and E is occurring only 9 times or 9,000 times. So, it is going to be its bit string is going to be longer, which is going to have 4 bits in it. So, if you see the encoding in the variable length, the character which occurs most frequently has a smallest length representation or encoding, whereas the character or the alphabet which occurs very rarely or it is not so frequent, its representation or its encoding is done by a bit string of relatively larger length. One can easily check that the variable length coding requires much lesser than the fixed length coding. The bits required are much lesser than the fixed length code schemes. One can easily verify that this works out to be this number. So, we see that if we use a variable length codes, then the size of the coding becomes much smaller relative to the fixed length coding. So, what we are going to do is try to see schemes in which we can define variable length codes for coding. One very important concept that we have used without noticing when we wrote down the codes here, the codes that we wrote down here has one very important property which makes it useful, and that property is what are called the prefix code. In variable length code, we must decide for each code where the bit for each character starts and ends. So, in variable length code, there has to be a method which is going to determine where the bits for each character start and end. So, for example, if you have a coding like this is a variable length coding. So, E the code is 0, for A it is 1 and for T it is 0 1, and we look at 0 1 and 0 1. So, we look at such a string. Now, such a string could mean, so E can 0 can be E, A is 1, so this can be, and this is T. So, 0 1 0 1 can mean it. It can also mean, it can be just also be T T, or so this is T, this is E and this is A. So, we see that if you have no way of deciding where the encoding for one the bit starts or ends, then we can have ambiguity in deciding what our bit string is going to represent. To remove this ambiguity, we consider what are called prefix codes. So, prefix code is a binary code such that no code word is a prefix of another code word. What we see here is E is a prefix to T, correct. E whose code is 0 appears as a prefix to 0 1, which is a code for T. So, in a prefix code such a case is not allowed. that is, no code word is a prefix of another code word. Once we have this property on a code, on a variable length code, then there is no ambiguity in encoding or decoding back the information. If we see the previous example, we see here that what we have defined in the variable length code is actually a prefix, is actually a prefix code. We see that in this no code is prefixed to another code. So, if you pick up anything 101, we see that it is not a prefix in this, neither it is a prefix here. So, we can check that none of the codes are prefixed to any other codes. So, this scheme of variable length is also a prefix code. Another crucial property of prefix codes or generally binary code is that they can be represented by a binary tree. In the binary tree that is going to represent a code, a binary code, each external node or leaf is going to store a character. So, all the leaves are going to store characters. The code word of a character is given by the path from the root to the external node storing the character, and with convention we will use that as we traverse left, we are going to label it as 0, and when we traverse right, we are going to label it as 1. So, in this binary tree, whenever we are going to traverse a left edge or edge to the left child, remember we are working with binary trees. So, we have a, for every node we can have a left child and a right child. So, the left child is going to be, edge to the left child is going to be labeled as 0, and to the right is going to be 1. So, one can label this like this. Once you label the edges by this convention, you see that for A, we are going to look, we are just going to look at the path from root to the leaf which is storing A. We are going to concatenate all the labels of the edges which are going to be on this path. So, A is going to be 0 0, B is going to be 0 1 0, and C is going to be 0 1 1, D is going to be 1 0, and E is going to be 1 1. So, a binary code can be represented by a binary tree. This observation is going to be crucial in constructing binary codes which are also prefix codes. So, the binary tree which is going to represent a binary code will have all the characters stored at the leaf nodes. The edges are going to be labeled 0 or 1 depending upon whether it is a edge to the left child or the right child. So, if it is to the left child, the label will be 0. If the edge goes from parent to the right child, the label is going to be 1. And the code word of a character is simply concatenating the labels of the edges which lie on the path from root to the leaf that holds that character. With this observation, we now look at an algorithm to actually construct prefix code. So, Huffman coding algorithm is an algorithm which precisely construct codes which are prefix codes and are of variable length. So, there is a brief history about the problem. Huffman in his college days actually worked out this coding scheme as part of his assignment. So, we look at the Huffman codes. It is a greedy algorithm and it constructs an optimal prefix code. That means, we cannot have a better solution than the one which is constructed by the Huffman algorithm or the greedy algorithm that we are going to construct or design. The algorithm builds up the binary tree in a bottom up manner. So, rather than constructing a code, we are going to construct a binary tree which is going to represent the code. suppose C is a set of n alphabets of which your text which we want to code is made of, and we know the frequencies of each character C, right. So, we know FC for every C in C. The algorithm begins with a set of n leaves, which is the size of set C, and performs a sequence of n minus 1 merging operations. A priority queue is keyed on f values to identify two least frequent objects to merge together. The result of the merge is a new object whose frequency is the sum of the frequencies of the two objects that are merged. The new object is going to be inserted back into the priority queue. Right? So, Huffman code is going to be a greedy algorithm. That means, we are going to start always working with keys that are going to have least frequencies and keep on merging them together. So, Huffman algorithm is going to run in time d log d, where d is the number of distinct characters of x. We are going to have a priority queue having d elements, because d is the number of distinct characters. So, we are going to extract and insert an element into a queue with d elements d times. So, that is going to give us a factor of d log t, right. At every step we are going to extract a minimum value from the priority queue, and once we extract, we are also going to insert back an object or element back into the priority queue. So, each operation of this extracting and insertion is going to take log d times, and we are going to do this d times. So, we are going to get a factor of d log d. The priority queue is implemented using a heap. So, we have a pseudo code for Huffman algorithm. So, in this algorithm, we compute, this is the function which computes the frequency for each C in C. Initially, your priority queue is going to be empty. We are going to insert elements in queue based on their frequencies. We are going to remove two minimum keys frequencies. We are going to merge them into a single tree, and going to insert back the sum of the frequencies back into the queue. This is going to be the Huffman algorithm. So, initially we are going to start with all the leaf nodes and step by step build a Huffman tree. So, let us illustrate this with an example. So, we have a text which we want to encode. So, we look at first the frequencies of the characters that occur in the text. So, the frequencies are here. So, we see that A is occurring 5 times, B 2, C 1, D 1 and R 2 times. So, the algorithm Huffman will start by writing all this as leaf nodes. So, the algorithm will begin by making all the leaf nodes and arrange them in a priority queue based on the frequencies. So, we see that we are going to now from this we are going to remove the keys which are going to having the least frequencies. In this case, the least frequency keys are C and D. These are going to be merged. So, we are going to merge them and create a tree, the frequency of which is going to be the sum of the frequencies of the trees that have been merged, and we are going to insert it back into the tree. So, we take the look at the next step. In the next step, we could merge this two, or we can also merge this two. So, if we merge this two, we get precisely this tree. Now, next, and if you are saying we are inserting them So, this is going to be inserted back into the queue and will actually, so when this is inserted back, this is actually going to come at this position, right. So, if you look at the algorithm, once we merge this into a single binary tree, we are going to insert it back into the queue. So, once we insert it back to the queue, it will go to this position. The key of this is bigger than the key of this. In the next step, we look at, we are going to merge this and this, and we get the final tree, and the coding is going to be, so this is going to be, this is right, this is left, so this is 0, this is right, this is right, this is right, this is left, 0. So, the coding is going to be, so A is going to be represented 0, B is going to be represented as 1 1 0, C is going to be represented as 1 0 0, D is going to be represented as, D is here 1 0 1, and R is going to be represented as 1 1 1. Now, we see that this is actually a prefix code. None of the codes that we have are prefixed of other codes. When we insert, we should always insert in the, so in this insertion this should have come here, and in this insertion this has to be inserted here in the priority queue. So, if you see this, once we join this thing, this element or object is going to be inserted back into the tree. So, this is going to be inserted back. So, we are always going to remove the two with the least frequencies and merge them. So, the greedy strategy is, we are going to always remove F1 and F2, the keys with least frequencies, join them and insert this joint frequency back into the queue, and keep on doing this until your queue is going to be empty. Once you do this, your Huffman tree is constructed. We have one more example. We have a string, and we have the characters that occur in the string. We see that A occurs 5 times, B occurs 1 time, and say V occurs 1 time. Finally, this is a blank space which is occurring say 9 times so the blank space is occurring the maximum time. So, in this case, so if you look at this, the blank is going to have only 0 0 as the prefix code, whereas V, if you look at V is appearing only once. Its binary code or Huffman code is going to have relatively a longer length. This will be 1 1 1 1 1 1. So, V is going to have 1 2 3 4 5. So, V is going to be represented as 1 1 1 3 4 5, whereas just the blank space is 0 0. Similarly, we can look at all, if you look at all leaf nodes, those are going to be the characters in our text. Look at the path and the labels of that path from root to vertex, that leaf vertex, that will give the code for that vertex. So, this will start first by putting all this in a queue, and then we are going to first start by doing say I and K. So, these are merged here, then O and S are merged, O has 1, S has also 1. So, O and S are merged here, and you are also going to merge. So, we keep on merging such things. Okay. So, as we first merge say this I k, it will go back to the insertion tree, then we look at O s and merge them again, and so forth. So, if you see, if we continue with the procedure, we will precisely construct a Huffman tree for representing or for encoding string which is given here. So, what we have seen is in Huffman coding we get a variable length code which is a prefix code, and moreover it also gives a optimal prefix code. Remember, we have seen already that we can have variety of prefix codes of say variable length or fixed length code. In the variable length code, if you have types of different types of Huffman codes or different type of prefix codes, then obviously we are interested in finding the code which is going to be best. Best in the sense it is going to use least number of bits to represent, or the number of bits that we are going to require to represent the text is going to be small. Thank you.